So welcome back to the class Computational Neuroscience, Neuronal Dynamics of Cognition. This week we work on continuum models, and this part now is the hard mathematical work where I will derive the spatial continuum model, the so-called field model. Now, the way we do this is we start off with a set of discrete populations, then we take the continuum limit, and I will show you the mathematical tricks that allow you to turn a discrete population into a continuous population, how to translate a set of discrete equations into a field model. So let's think of neurons in the cortex responding to different preferred orientations. So for example, the neurons here would have a preferred orientation theta 1, the neurons here would have a preferred orientation theta 2. Now, if I walk along the cortex, I can also take this axis as a spatial axis. It's sort of equivalent. The location of the neuron is also an indication of the orientation, and in the following I will use the notation with the spatial variable x. So the way we proceed is we start with discrete populations. I start at 0, then I have here a delta x, I have here 2 delta x, I have here 3 delta x, and all of these populations should have roughly equal size. And then I can ask, what's the activity of one of these populations? For example, this population here. The activity of this population is the population n, in this case it would be n equals 3, and I can define this activity as a function of time. Similarly, I can ask what's the membrane potential or the input potential of this population, and it will be the population at location n, and it is the time-dependent input potential. And then I can ask how many neurons are inside this group, and I call this the group size, and this is nn, the number of neurons inside the group. Now let's look at one of these populations. I look at population n, and I write down the differential equation for this population, tau dt dt hn minus hn plus the total external input. Now, the input can arise from interactions within the same population. So this neuron here talks to all other neurons with a connection weight WNN. But this neuron also receives input from a neuron outside with connection weight NM from population M to population N. And now basically I would like to redo the calculation I did at the beginning of this week's session. So let's copy here this part. Then the total input is the input that's really external, really outside input, an input coming from the outside, which I call external of t. Then there would be input coming from inside the same population, and then there would be input coming from other populations, and I sum over all these other populations m. I can copy the first part, and now for the interactions, the current that's coming from inside this population, we did the calculation before. I can just repeat it. So this current would be the sum over all neurons that are part of this group N, of this population here. Then we sum over all the spikes, and then each spike contributes a synaptic current T minus TJF, and these interactions come with a weight WNN. This is my WNN. Now, the input coming from other neurons follows completely analogously. So I sum over all the other groups, and for each group, I sum over all neurons J that are part of this group. I sum over all spikes. I will have weights, W, N, M, and I will have current pulses, T minus TJF. But we know what this is. This is the sum over all spikes of all neurons in that population. So this is just A n of t minus s with an integral alpha of s. Now you should remember that the activity is actually the sum over all spikes, all neurons, divided by the number of neurons in that population. If I don't divide by this number, I have to multiply out. So now this is all spikes, all neurons. And then I can copy the weight in front, WNN. And I can do the same thing for the other populations. Sum over M, I will use the weight and put it in front, WNM. And then this gives AM of t minus s, alpha of s, integral, there should be a ds for both. And I still have now to add this number nm. So this is the sum over spikes of all neurons in the other population M. I can copy the rest, minus hn plus external of t plus. Now you see that I can really put these back into one single summation, sum over all populations, including m equal n, and write it down as WNM. I leave a little bit of space, and then I write alpha of s am of t minus s ds. I left a little bit of space because I still have to work on the group size. So let me just add this number here. And then I have to copy the rest. So what do we have now? We have a sum over different populations with different population activities, and these drives the evolution of the population activity at location n. So we are still discrete. I still have my discrete populations. And now I do the actual continuum transition. Instead of talking about the population number n sitting here, I will give an index to the population for this location, and the location is x. So I will call this population here the population which sits at the location x, where x is n times delta x. So this population would be the population 3. So this is then my value x, and the whole thing is still dependent on time. Similarly, for the membrane potential, I will make the transition. This is the membrane potential at location n times delta x. That's my new value x, n time t. And for the group size, well, how many neurons do I have inside? Well, this is now very important. I have chosen a value delta x, which is completely arbitrary. I could have chosen a smaller delta x, say half the size. This is my new delta x. In which case, well, I have only half as many neurons inside as I had before. So I can introduce a density of neurons, and then I write times delta x. All populations have the same size. If the density is constant, then the number of neurons just the density times the delta x. There's one more thing. I have these interactions. The interactions are WNM, which is the interaction from M to N. And I will write this now as interaction between N times delta X and M times delta X. Or, if I call this X, it's the interaction from location X prime to location X. And so now let's take our discrete differential equation and rewrite it in terms of these new variables. So now I have tau d dt h, but hn is h at location x. At location x. It's the external input, which could be different at different locations. So let me just add this. This is the external input at location n, at location n, at location n, which makes it at location x. And now I sum over m, including m equal n. My w is w of x and x prime, using this expression here. My nm is delta x times d, and this curve I copy alpha of s, but I replace the m by x prime at location x prime t minus s ds. This is still a discrete equation. We started with a certain delta x, the blue one. Now I changed it, the pink one, which is smaller. I could change it again and make it even smaller. And each time the number of neurons inside one of the populations will decrease. So it's this factor delta x which is very important. At the same time, the number of populations will increase, because in the end I always have I have to cover the same total spread of population material. So you will see that this delta x allows me to transform this sum into a Riemann integral dx. And this is then the final equation. Tau d dt h of xt equals minus h of xt plus I external xt plus integral dx prime wx x prime alpha of s a of x prime t minus s ds. Okay, this is the status of the slide at minute 12:58. So now I have one equation for the whole spatially extended population. And this is an equation which has an integral on this side and a differential on this side. So it's an integral differential equation. And this equation is also called the field equation, or it's the continuum equation for my population activity. There's one more step we need to take. We still have the population activity on the right-hand side of this integral differential equation. But the population activity is in this limit of high noise and slow transients. It's just a function of the membrane potential. Therefore, I can close the argument and put here my function of the membrane potential for the activity. I did one more thing, and that is I replaced the w of x and x prime by w of x minus x prime. And the idea is that it only depends on the difference between the two locations. So sometimes people even write explicitly difference between x and x prime with the absolute values, which I can also put in here. So one field is one integral differential equation. The whole thing is a field equation or a continuum model. The first one, or amongst the first ones, were Wilson and Cowan in 1973. These models have been very popular. These are essentially population activity models as a function of space, but the variable x can be space or something else. It could also be an abstract quantity such as the preferred orientation of the cells at location x. So I haven't really talked about the interactions. I said we can take it as a difference, and often this difference is such that locally you have excitation. So within a group, if you think in the discrete way, within a group you have excitation, but over longer distances you have inhibition. And this is bidirectional, so neurons here would inhibit neurons there, while this neuron here would excite the neuron there. It's also called a Mexican head for obvious reasons, and it means local excitation combined with long-range inhibition. Now, in the brain, there's a separation between excitatory and inhibitory neurons, and importantly, inhibitory neurons mainly have local interactions. They talk to their local neighbors. So in order to get effectively a long-range inhibition, one way to think about it is to say the excitatory neurons excite inhibitory neurons at some distance, and these in turn inhibit the excitatory neurons there. So that overall you would have an inhibitory interaction over long distance, despite the fact that inhibition itself is local. So let me summarize this part. This was the hard mathematical part. I've derived field equations. And what are field equations? Well, these are population activity models in the spatial continuum. The coupling is taken as distance dependent, and importantly, these models work best if you say the activity is just a function of the input potential, which essentially means that we work in the limit of high noise. We have slow transients. Now in the model we have this distance-dependent kernel, W of x and x prime, which assumes long-range inhibition, but that's just a summary of the effective interaction between excitatory and inhibitory neurons. The variable x can represent the space itself or an abstract variable, like the theta of the preferred orientation. And in the following sections, we are going to use this field equation repeatedly.